Okay. Hi, everyone. Good morning. Thank you so much, my professor, my beloved professor. It feels like a family today for two reasons. One is that, first of all, you invited me for a second time this year, and I'm really grateful for this opportunity. I'm feeling really honored that I have this chance to share with you the work that we're doing in IBM Zurich Lab. And the second reason is that, as my professor said, that there are so many people here that I want to thank one by one. We don't have the time, but definitely whatever I have done until now is because of this family that we have in the microlab that Mr. Professor Sudris created, and I'm really, I own everything to my professor and to that family of those people supporting this lab. So thanks a lot, and let's start with the first topic of this conference. Of course, I'm going to talk about the Great CHIPS Act, right? We talked a lot about the CHIPS Act, right? We have a CHIPS Act in Europe, and I want to describe the journey from the silicon to what we have today, which is the thinking AI. Maybe many of you have used ChatGPT, DeepSeek, other models, that they have this loading button stating thinking. Is it real thinking, or it is something else? Maybe simulation of thinking. This we're going to find out until the end of the presentation, but I want to take you on this journey towards that technical part, and also mention the technical achievements that we are doing, and we are trying our efforts in our lab in Zurich. So let me start, of course, with a disclaimer that everything that I'm sharing with you is my views from what I'm going to share with you. And this is very important because it gives me the flexibility, as we have also in research, right, to think widely and be able to imagine what is going to be the next frontier of computing, right? And this is why this talk is not about a specific product, but is about overall how we perceive the next wave of computing. And it's not only myself that we are envisioning this. We are around 3,000 researchers across the globe in 19 locations, in all over the 6 continents across the globe. And over the years, they've been impressive awards from IBMers, like 6 Nobel Awards, 10 Medals of Technology, 5 National Medals of Science, and 6 Turing Awards. These are impressive awards from this community. And specifically, my lab in Zurich was established in 1956. Back then, most probably was the first one on the high-tech company having a research lab in Zurich. We are more than 45 nationalities, which gives me a nice excuse to not speak Swiss German. It's very difficult because one way or another we need English to communicate. And we are having a very open collaboration, attitude. Up to now, we have more than 50 funded European-funded projects from Horizon, and more than 500 partners, right? And all over the years, notably, there are 2 Nobel Prizes by 2 IBMers in 86 and 87 awarded for the invention of the scanning tunneling microscope and the discovery of high-temperature superconductivity. This is a European Physical Society historical site. It's a very beautiful place to work, and we are very excited to work on that lab. Let me start, right, with a little bit of history, right? And I've mentioned thinking before. I think it's the best place to talk about thinking, right? Because we are in the place that Plato, right, was actually thinking and trying to take a philosophy aspect of the life and so on. And let me start 2 million years ago, right? Which is, okay, we're going to be fast, right? So don't worry. But just stating that in the Stone Age, people at that time, right, they had created tools in order to make progress. And those tools, eventually, they have to be evolved, we had the tools evolution from one tool to the other in order to be able to make progress, okay? Eventually what happened later was that it was not only about an evolution of the tools, it was only at some point transformation of materials. People, they have been in need to transform material to get to another level of productivity. So we've been from the Stone Age to the Bronze Age to the Iron Age and so on. And then eventually we have managed, the people, they have managed to transform the energy, right? And harness the power of the water, the steam engine, the electric power, the combustion power to reach the newest, the latest years that we have managed to transform the information. And eventually, this allowed us to create computing systems, create knowledge and algorithms, and be able to create a huge progress over the x-axis, the y-axis, right? But as you see, the horizontal axis is also logarithmic, right? That means that at the time that we've been able to make not only an evolution of the tools, but a transformation of the material, the energy, we've been able to make huge progress and very, very fast. This is why the last years we are feeling, right, that the technology is running so fast. And I want to submit to you that today we're in a phase that we're transforming something else. I will reveal by the end of the presentation. All this technology has been achieved, right, by, first of all, making a question. All these tools that we have developed, we first of all made a question, we study, we create a hypothesis, right? And then we tested this hypothesis to assess the results and make a report. All this in an iteration loop. This is called the scientific method. And we do believe, I believe, that the scientific method is humanity's best model for discovering new things, new materials, new technologies, right? And if we take an example from the past, right, we have seen that always that was the case when people made great progress, right? Always it was about scientific method that people were able to make a progress. For example, with Pasteur, Galileo Galilei, creating those impressive instruments, groundbreaking instruments to make a huge progress, okay? So from the telescope to the microscope to the particle collider in CERN, all these are groundbreaking instruments. And I do believe that today we are about to discuss, and this is the agenda for the talk, about evolution of some tools and also transformation, which is different. We need a lot of evolution to be able to reach a level to transform the material or the energy to get to new progress and new achievements. Saying that, first of all, we have, in IBM, we have our technology atlas, which is highlighting all the evolvable tools that we need in every sector of the technology, from AI, automation, data, hybrid cloud, quantum computing, and security. Each one of them has a specific part of tools that we evolve. But today, apart from this evolution, we are experiencing the two largest transformations in IT, I believe, over the last 30 years. And these two are agentic AI and quantum computing. Let's start with the first one. So, agentic AI, how we've reached to this agentic AI that also we think that is called thinking AI. First of all, we had our traditional AI models that were actually siloed models. Each one of those models, for example, to train, we had a specific domain. We had text only, we had video only, we had music only, and so on. And people, humans, we needed humans to create labels so that we can create training when we had human annotated labels, right? This is how we created all these individual models. But this was too slow because people, they needed to be in the loop to make this labeling, and this is getting too slow. This is where we had these emerging foundational models that have been able to grasp raw data and find the correlations themselves without needing this labeling. And this allowed us to automatically give to those models a lot of modalities in raw data format without labels, and by understanding the inherent language of what we give to them, they've been able to predict the next and the next and the next word. This is how foundational models work. And eventually we've reached today the next wave of AI, which is the agentic AI. That is the case that these models, these foundational models, not only they rely on plain text or plain video or plain music, but they are able to create tags, if you want, right, to understand the use of a tool. So we can give them the ability to use a tool by specifying the grammar, if you want, to say, for example, JSON or something else, to use a tool to do something, search the internet, make a purchase, doing something else, for coding, for example, and so on. So by giving this capability to those foundational models, we're able to automate the process of interacting with each other and achieving a final goal. And this is what is called agentic AI, the combination of foundational models with tools in an automation manner. Of course, how we have reached this and what happened in the last maybe 2 years to 3 years maximum to get from foundational models to agentic AI is mostly highlighted in this figure, right, in this slide that is very dense. And I have it dense for a reason, because I'm not going to refer to all those details. We need maybe a single workshop to even get over some of the very, very abstract details of this one. So, but these are very, very important. For example, with the blue line, I have highlighted some that are maybe breakthrough innovations that allowed us to go to agentic AI. For instance, when it comes to the models themselves, we've been able to root the skills, meaning that something that we have in our society as well. We have experts doctors, we have experts electricians, we have experts programmers. We gave to the models the same capability to root the skills. We had one skill for the code, one skill for the math, one skill for how to use the tool, and so on. And this is called mixture of experts models. Today, most of the models out there are mixture of experts. And for instance, another example is when we train the models in the second part, right, where we have been able to learning without human labels, and also auto-generate chains, critiques, and unit tests. This was happened with synthetic data. Today, most of the models are trained with synthetic data. Of course, real data, human data, but we are using a lot of synthetic data to train our models. And at inference time, we had what is called tree of thoughts, right? Which is something that we are also, humans, we are doing. We have a lot of thoughts when we are talking to each other. We have one thought, but at the same time, we're thinking something else at the same time, right? And we give to the models the same capability. This is why they're flexible at runtime and they can select different paths. And if you ask again and again and again, they're always selecting maybe a different path with some probability. And also when it comes to the system level, where many people are working, right? On the system level, there is a lot of innovation happen. For example, when it comes to the memory, how we architect the memory. And again, we took example from humans to train those models by creating different layers of memory, like episodic memory, right? These are words that haven't existed before. These are new concepts that we give to our systems today to run those models. When we write something on ChatGPT, it relies on all these technologies. And we have memory systems with episodic memory, semantics, task memory, vector databases, whatever. So it's a lot of innovation that happened that allowed us to get into the agentic AI world that all of us enjoy today. However, let's see what we have succeeded so far and where things are going, right? This is a figure showing what we should expect by 2030 when it comes to the AI capabilities, based on all these agentic innovation and the one that we expect to come. And it shows over the time axis that all those dots are real examples of what the state-of-art models have succeeded so far. And it states that when it comes to software engineering, today we are at a level of almost 80% to solve the most difficult software engineering problems. 80%. This is insane. This is amazing that we can increase our productivity when we rely to such tools. However, if you ask me, you have to really be still a very good programmer to get advantage of these tools. Because if you are a medium kind of skills programmer, probably it will take you more time to realize what the model is doing. And this is why many companies are complaining that they don't see the productivity by having those tools. If you are a good programmer, you take a lot of productivity advantage. However, in benchmarks, we see that they solve the 80% of the most difficult problems. Also the same for biology. They can solve problems in the biology domain at the level of 40%. Biology is a very difficult domain. And the same with the frontier mathematics, which is a huge, very difficult domain as well. And these curves, they show that by 2030, probably, right, with what we explore today, we're going to have systems that they have solved all of our most difficult today problems on those domains. Of course, there are other domains as well, and we have foundational models for others, but this is just an example. However, how we succeeded to that was because of a lot of capital investment, a lot of money that was invested to have those huge data centers to train again and again those models and be able to deliver this performance. For instance, you see that the hardware cost of the leading AI supercomputers has doubled every year. It runs with 1.9x every year the cost to run such a leading AI supercomputer to be able to compete at the top level, okay? And so it's, of course, about capital investment, and at the same time, let's see, we have seen what they've succeeded to, but at the same time, where they fail. Maybe all of you have realized that sometimes they fail to manage to deliver what you want to have. And a famous example is this one, is a paper that you can read. This is really nice to read, the LLM cat attack. In that particular example, what the authors they have done was to add a random trivial phrase. For example, you can give to a model an interesting fact that the cats slept most of their lives. This is it. And then you can continue your prompt, whatever you are looking for. In most of the cases, because of this statement, most of the today's frontier models, they will make a lot of errors. And for example, they can triple the error rate to maths. So you try to solve a mathematics problem, you just inject it with a phrase relevant to cats, which has nothing to do with maths. And still the model fails by 3 times more to give you the right answer. So this is a kind of, we're living in a timeline where the cats sleep a lot is classified as an adversarial attack. So that means we don't have good guardrails of our top frontier models, even though we spend so much money for them. At the end of the day, all this thinking, we see all this thinking, right, to deliver all of those results, is really thinking or a simulation of thinking? And I've asked all of those models that you see on the left-hand side, the top-tier models, Clouded, GPT-5, Grok 4, our internal models in IBM, Granite, which one of them is, what eventually is AI, what AI is doing? And the response was that thinking is about conscious, goal-driven, subjective understanding, and adaptability, which is fine. However, simulation of thinking is just generating responses that fit patterns of real thought and language use, but without being aware, without comprehension, and without purpose. I think this is what is the big difference between the thinking of simulation and thinking. And I submit that today's models, they are simulating of thinking. Anyway, this is why in IBM we are trying to create models that don't fit every purpose, and we try to create models that they fit the enterprise domain. And that means that they have to be accountable. We cannot give a model to an enterprise, right, as a company, and the model not being accountable from what decisions it took. And this is very hard as a problem, but this is what we're trying to solve. And we have created our own models. We have, under the product IBM Granite, there are open source models available in Hugging Face, and we have a lot of models for different, scope, language models, vision models, document conversion, speech, time series, guardrail, embedding, and geospatial with collaboration with NASA and ESA to be able to deliver what the enterprise needs. And for instance, as I said, we have fully open source models, meaning all the weights and the architecture are open. They are very performant, and I have a slide for that, and they can be trusted, right? They can have guardrails that make sure that the model will behave as it should. And how we verify that is by being the first, for the fast forward, but being the first company that we have an ISO for that Granite models, is the first ISO coming up that verifies that the model will behave as it should. And the architecture is based on a lot of different novelties that I've mentioned just before. For example, it is a hybrid model, meaning that it's not only transformer, because transformers, they're great models, but as long as the query that you type in, for example, you have a code and you want to give you the full code, okay, 2 pages, 10 pages of code, the more you add in, exponentially is the memory requirement. So there is another architecture of models called state space models, and these models, they have a linear requirement when it comes to memory, but then the performance might be affected. So we've tried to create an architecture which is a hybrid architecture that brings both two worlds together, and then we have the benefits of not sacrificing performance and at the same time scale very well when it comes to the memory. We have other novelties like no position encoding, but these are getting too technical to explain right now. But the purpose of those models is to be small and be very efficient for your purpose. We don't want to create a huge model, right, to compete the generic knowledge. We want a model, for example, for accounting. We want a model that we do with collaboration with NASA to create a model for climate, right? We want specific purpose models, and that ones, they are much smaller, much more efficient, much less cost to train. And when it comes to the performance, we have shown, for example, here is a diagram showing the estimated memory requirements on the x-axis, on the y-axis, the average accuracy, and you see that our models are top position when it comes to other leading models like from Meta, the Llama, the Mistral, the QWEN from Alibaba. So you see how much more performant they are when we can customize to the domain of the enterprise that we want, and not spending millions, right, to train and, of course, to have a huge model to consume energy and so on. And we managed to do that by eventually taking raw data, as many other models are doing, but filtering them out with a lot of stages that at the end of the day, we have only what we want for our domain. This is the ISO certification that I've talked about, the 42001, which is one of its kind, if you want, at that time right now. There are not many models that you can find that they can be certified for the enterprise world. This is why, of course, we wanted to share our knowledge. As I said, all those models are open source. You can hack them, you can take the weights, you can take the architecture, use them where you want for, and we want to share this knowledge with other people. And this is why 2 years ago we created the AI Alliance with Meta, with many companies and many universities across the globe, that we want all together to create models that are open source, you can trust them, and you can verify that you can use them safely on your environment. This is the alliance.ai that you can find more information about this consortium. So right now we do think, I think most of us, right, that AI needs compute and data. Is it really what AI needs? And I want to propose that, for instance, when it comes to the data part, what we see here is that very soon, by maybe 2030, will be run out of human data. The models will consume everything that humans generated over the history. And this shows that this trend keeps well. Even if we take the green line, that we take into account that, of course, the estimated stock of human is, of course, increasing, but still, we're running out of time. However, in the training of the models, we have methods that we can use very efficiently synthetic data, data that are generated by other models. And we can use them not only for training, but also during the evaluation. Because during the evaluation, we also need what we call LLM as a judge. We need other LLMs to judge our LLMs and generate metadata that through reinforcement learning, we are able to make models better and better again. So I would propose that maybe data is not a huge problem. We're going to have data. But computation is, of course, challenging, and we need chips, we need the semiconductor innovation to deal with the computation needs. For instance, this is from the talk of Jeffrey Hinton, that he was awarded last year the Nobel Prize, stating that all this experience that we have seen and the boom of the AI was because not of the data, but because of the increase in computing power. And so on, from Professor Thorsten Häufler in ETH, stating that computation is the new oil. However, apart from computation and data, I think most important is that AI needs watts and water. And we need it for two reasons. For the upper part, you see that, of course, when we run our models down there, we need electricity to feed all those accelerators and systems and storage and everything. But, of course, we need to dissipate the power with water. And at the same time, we have another loop that comes up, which is the power to dissipate because of cooling all those systems. So what people are doing these days to solve these problems? Some of them, and these are really new results, I think it was like 2 weeks and 1 week ago or so. I have the date, right? China, what they're trying to do is to take the data centers and put them at the bottom of the ocean. Okay, then they can use the heat sink, right? The ocean as a heat sink to dissipate the power. The same happens with H100 GPUs that some companies on the private sector, they want to send them to space. And then they want to have an infinite heat sink. This is their product marketing, which is fine. Nothing bad about those solutions. But probably this is like a bottom, how can I say, it's not a top-down, it's a bottom, is a top-down, right? I mean, it starts from the system. It takes the H100 as it is and tries to put them either deep in the water or in the space. There is a reason behind that, because we can find renewable energy, for example, in the space from the solar, in the bottom of the ocean from wind parks in the ocean, and so on, and this is their main claim. However, this is not solving the problem from the bottom. And at the bottom, we have to solve the system. For example, this is a figure showing in the y-axis the total electricity being consumed, and the orange line, sorry. Okay, the orange, yeah, pointer, I don't have. But the orange line shows the typical system today that consumes 10 to the minus 14 joules per bit, okay? That shows that very soon we are on a trajectory that the data center workloads, they will consume all of the world's current electricity generating capacity within the next 15 years. That means that we need at least 3 orders of magnitude less energy per bit that we transmit, okay, to be able to push this envelope for another decade. So to be able to show that in 1 decade, we're not going to have a problem with that. Except, of course, if we find other sources of energy, like nuclear energy, plasma, we'll see. But this is what it is reality today. And pushing this envelope 3 orders of magnitude means that we need almost to reach the capability of human brains, the efficiency of human brains, which are in the order of 10 to the minus 15. This is a very challenging project to deal with, and of course, there are some innovations happening at what we call, no, but I cannot proceed with, maybe stuck? Okay? Okay. Yeah, okay. I cannot control, but yeah, we can communicate. Thank you. And what happens is that today, our CMOS efficiency is at the order of 10 to the minus 16, meaning, as you see on the left-hand side, meaning that what even the best possible that we can do, we cannot push this envelope with our current CMOS technology, maybe. And of course, there is a lot of work related to adiabatic computing, which is what we call, there is always a device limit of how much power you need to reverse from one state to the other. This is called the Landrut limit. And there is a lot of work on that side, right? For example, when we're about to do calculations, we can dissipate the power to not push it to the heatsink, but we can use it to do actual calculation. Anyway, can we please proceed? Okay, that means, and this is a figure showing the peak power over the peak performance. And this is for many, many different systems today, different form factors, from chip level to card level to system level solutions. And as you see, all of them, they are in those red lines, they show the joules that we need per every operation. And today, we are very, very far from where we need to go to push that envelope. This is the goal, 10 femtojoules per operation. But funny part is that if we check our calculations today, we have 20 femtojoule per operation, and we need 1 or 2 times of order of magnitude more joules to just bring data from the memory. So that means, can we proceed? That means that we need to do a lot of innovation at the technology layer to be able to, as I said before, from the bottom up, to be able to harness this, this innovation, okay? And that allows us, this is the full stack from the physical layer to the technology layer, to the architecture layer, to the software layer, to the cloud layer, and then to the agentic AI layer at the top, to be able to offer different top-end solutions. Okay. So this is why IBM introduced some time ago the 2-nanometer node chip that was established at the IBM Research first, and now we are commercializing this technology This, of course, was a much more efficient technology, 75% less energy versus the 7 nanometer node and 44 more performance. But this, of course, we have to prove it when it comes to a real foundry, okay? And this is why we collaborate, if we go to the next page, please, with the nation of Japan to be able to create the first foundry for this type of technology, which is in collaboration with a company named Rapidus. And the all innovation around that is the gate-all-around nanosheet transistor, and this is the facility of this foundry in Japan. So eventually, that was our way as IBM to make, you know, the 2 nanometer technology reality in a foundry that will compete the worldwide foundries of Intel, Samsung, TSMC, and so on, and we're very excited to succeed on that journey. Next slide, please. So when it comes to the information representation, today we have bits, okay? So we have 2 states to represent the state, 0 and 1. And if we proceed to the next, have a lot of animation, and it's, yeah. And the same if we want to, you know, depict different states, 0, 0, 0, 1, 1, 0, and we need 2 bits to represent the 2 states. This is an example with Lego, the simplest example. So can we go next? How can we build a city out of this, okay? Let's go next. So we can have a building table, which is our, you know, CPU, right? And we have a store, which is all of our Legos, and we can bring back and forth. This is what we do today. And in this slide, we have the ability, we are coming up with an ability to have the same system, CPU and memory, at the same place, so that we don't have to go back and forth, but at the same place that we store the data, we can do computation. This is called in-memory computing. And we are pushing a lot from our lab in Zurich. Next, please. This is the overall idea. In the upper side, you see the von Neumann architectures that are moving that data back and forth from the memory. And what we propose is to move the data to the memory. And then you, of course, need, again, a control unit to do all your orchestration, running your code, and so on. But this is not the mandatory, right, to run your very, very heavy operations. We run the operations in the memory. And we can do it with different types of devices, SRAM-based, DRAM-based, flash-based, resistive-based, phase change materials, and other materials, magneto materials, and so on. Next one. We can also go to the next. And by doing so, we can eventually create matrix vector multiplication units, right, that we can use the weights, the memory, as the weights of our neural networks. And on those weights that are stationary after the training that we have done, we can take advantage that the weights are always there, and then we can do the computation for these deep neural networks in place of the memory. We don't have to go to the CPU and memory back and forth. Always the computation is done in the memory. And next one, please, and the next. And doing so, we have shown that we have been able to build 2 chips that eventually they are based on this in-memory computing. In the first case, we have 64 tiles of 256 by 256 crossover arrays. In the other side, we have 34 tiles of 512 by 512. And we have fabricated those chips, and we are measuring what performance it is and consider them to get to a product, right? But this is at least what happened at the research level. We can go to the next. Don't have another way And what we've succeeded, because this is something that I've shown also last year, but this is something new that we haven't done at that time, is how we can take advantage of 3D layer memories, okay, to map the most sophisticated neural networks that we have today, this mixture of experts, in such an architecture of in-memory, 3D in-memory computing. And what we have measured so far is impressive. 6 times increase in throughput, 20 times improvement in the area efficiency, and 1,000 times efficiency in energy. So before sending our accelerators to space or to deep water, maybe there are opportunities to deal with where we are. So this is a very exciting project that we're working on right now because, of course, 3D NAND memories, they have some deficiencies. You cannot always use all the layers at the same time. We have some limitations, but this is why a mixture of experts is perfectly fine for that because we have one expert at a time, and this is how those models work. They need one expert. They don't need the full DRAM to work at the same time. So it's a very natural fit. Next one. The same concept of in-memory computing now can be realized with photonic in-memory computing. So instead of having the representation of the memory with bits or analog domain, we can have photons that represent the different states. And this is a work that is being driven right now in the lab when it comes to use the light as the source of in-memory computing. Okay, it's the same concept, but with light. Next one. Okay, we can proceed to the next because I'm going to talk right now about agentic AI. And today in the agentic AI, so we have been from the technology layer to the agentic AI layer. And today we do realize a huge problem when it comes, we call it the 1% problem. The problem that enterprises have today is that most of the open data, they have been used to train a model. But this model does not has less than 1% what enterprises they have in their domain. If you're a company, you have your own data, and those data, they are not represented in this model. So how can the model be efficiently used by your company? And this is called the 1% problem. We can proceed. And the reason how to deal with this problem is that, of course, if you want to adapt the model in the horizontal axis, yes or no. In the vertical axis, if you want to use external knowledge. And then we have these options here, how to deal with that problem. The first one is to do prompt engineering, which is probably not the best when it comes to the accuracy. And as long as your data increases, you have a lot of data, prompt engineering cannot give you a nice an outcome. We can have fine-tuning to fine-tune the model, which is very expensive to do. But we can also have what we call retrieval augmented generation, meaning that we can give context to the model by our knowledge inside our enterprise, inside our university, right? So that it can use this context to generate responses. And of course, we can have hybrid solutions when it comes to that. Next, please. So when it comes to the fine-tuning, we have different options either to create small models to fine-tune for every domain, or create a unique model based on what we have as a technology, open source technology called Instruct Lab, that we can instruct and customize the model by adapting new specific skills and knowledge. Next one. And today, most RAG systems, they rely on a complete isolation between your, let's say, the database that you have all your data. Okay, this is the lower part of the diagram, and the upper part, which is at runtime when you want to issue a query. And these two, they are not coherent, meaning that today what happens is that you have your data, you embed your data to create number annotations so that you can efficiently search after that, and create this vector database that you can query afterwards to get a response which is relevant to your domain. And these systems today, they do not talk to each other. So what we propose from our side, and next one is that we bring them together, and we call this content-aware storage. We bring those solutions together so that at the same place that you have your raw data, you have also your embeddings, and when you add, remove, update files, instantly the embeddings are being updated as well to reflect and allow the model to have the most updated knowledge. For example, I'm changing my home address, instantly the model should know. Should not be a latency that relies on ops, AI ops, ML ops, whatever you want to do that for you. The model should be able to pick up the information instantly and update the model with that information. And this is what we propose. Next one, we have shown this to the, so the idea is that eventually we change the storage in general, realizes a huge shift today. From bits and bytes, we go to content insights with this technology that I've just mentioned. And this allows us what we had before, native storage, block storage, file storage. That was evolutionary steps. But today, we go to a breakthrough technology that allows us to take content immediately by having metadata associated with our data. And next one. So this is what we've shown and shown to NVIDIA conference, GTC last May. And here you can see how all these components are coming together. This is a collaboration with NVIDIA to make this reality. Next. Of course, I think that we don't have the time to cover all the details, so we can proceed. I mean, just to mention here that the most critical component of a RAG solution today is what we call similarity search, being able to search similar vectors. This is what you need to do efficient RAG solutions like the one that I've shown before. And for instance, if I have 3 domains, you can have 3 dimensions. You can search, for example, for an apple because the apple is close to a banana. So when you're searching an apple, you're also getting the response that a banana is somewhere there because it's very, very close, right? But imagine that today our top models, they have 500, 1,000 dimensions. So they have a lot. And we have to speed up the process of similarity search. How we do it? Second slide, please. Next one. And the next one is we have created, and this is one accelerator from IBM, the Spire accelerator that was initially and still being used as an AI accelerator. And however, we have repurposed the accelerator to also do similarity search. And we've been able to show, that was maybe the world's first, that we could search 1 billion documents with 100% recall, meaning that you can search all those documents without sacrificing any accuracy. So even if you search 1 billion, you will always find the one that you are interested about. And this one has less power per query than CPU and GPU solutions that we have used. At the same time, of course, we had another work that we could also search 10 billion vectors, but then accuracy is sacrificed by 90%. So that is a trade-off. But anyway, that was an approach with an established chip by IBM, this Spire accelerator, to research very, very fast documents. And on the next slide, I'm showing what we are doing from research side, because that was a product of IBM, Spire. But from our side, what we are doing and working on heavily the last months was this vector search module that eventually is using the capabilities of modern FPGAs to, this is an FPGA embedded with a storage device, an NVMe storage device. And we go to this storage device and we add extra capability to do similarity search down to where the data live, down in the storage. This is a very impressive work showing a huge potential. We can go to the next slide. And we have measured these capabilities, showing that we can search 1 billion data sets from archive with very high throughput, as you see on the right-hand side, compared to FICE. Solution FICE is the best algorithm from Meta, and we can have very great efficiency when it comes to the throughput when we are using these VSMs. multiple of them. A single one, of course, cannot compete, but multiple of them are allowed to give us this extra performance. And next one, this work was presented to the Flash Memory Summit. And finally, of course, I've talked about 0 and 1, the two representations that we have today, but of course, there is an emerging topic of being able to represent 0 and 1 at the same time. And if we go to the next, this is the so-called quantum computing that allows us to eventually take advantage of the quantum computing to be able to, with superposition and entanglement, these are the two main vehicles that we're able to realize the quantum computing. If we go to the next slide, this is something which is not theory. This exists today. IBM opened first data center quantum supercomputer, right, in Europe. We do have an open space that you can go today and experiment with quantum circuits, right? This is not just theory. This exists. And if we go to the next, and I'm finishing very soon, we have shown just a couple of weeks ago that we could eventually collaborate with HSBC and show that we can, in trading, we can beat the market, but this, of course, was with historic data, not real-time data. We need a lot of work to go there to real-time, but we've shown that, I'm not expert in trading, but I know from people there talking that if they can beat the market by 2%, they can take everyone out of the market. So this work showed that they can beat the market by 34% by using quantum and classical computers at the same time. That was announced 2 weeks ago. And the next one showing, that eventually what quantum computing brings is that the classical computing with transistors, eventually, for every time that you need to double your power, you need to double the number of transistors. But on the right-hand side with quantum computing, what happens is that every time you want to double your computing power, you just have to add 1 qubit. Okay? This is the impressive thing about quantum computing. Next one, please. Yep. Okay, we can maybe just stating that while 30 qubits, we can today realize, with just the computational power of the laptop, the complexity increases combinatorially, which means that with 48 bits, we need probably the biggest, very big supercomputer. And if we connect all the classical computers on Earth, we're gonna be able to simulate 60 qubits. But we really need more than that to realize practical applications. For example, we need 200 qubits. And this is, for example, our IBM project named Starlink. We're gonna try to make it happen. This is for our target for 2029. And next one, we have already, I've mentioned qubits, right? But eventually all those qubits are not, are qubits which are they don't have errors. And this is the big problem of what we have today with quantum computing. And we have already presented in Nature, in the Nature, very prestigious journal, right, works, how we deal with error mitigation and what we do with error correction. And this is an active area that I'm working also in the last months, that we try to take all the knowledge that we have for classical error correction code and apply to quantum computing, because we want to have error-free qubits. And this is very hard problem today. Yeah. We go to the next. And of course, quantum computers are not gonna replace classical. They are gonna operate together. And this is our view of the future of quantum supercomputers, bringing together classical computers and quantum ones. In such a topology as you see here. We're gonna still have GPU supercomputers, data centers with GPU, data centers with CPU, connected with quantum supercomputers. This is at least our view. We're going to go to the next. Of course, not, as I said, all the problems can be solved with quantum computing. There are problems that we think, that we hope, maybe, to solve, like applications in chemistry, in materials, in machine learning optimization, because those data sets that we have can very nicely be represented in the quantum space, as opposed to make discrete quantization of the quantum space to the classical space and represent everything with just some vectors. It's better to represent the problems of where they exist, and nature is quantum. So we do believe that we have a roadmap. It's a very populated roadmap today where you see all these green ticks, but we have in the top part is the product roadmap. In the lower part is our technology roadmap, what we need to solve to achieve the products that we claim. And all over the years, at least IBM were able to deliver what we've promised. And we hope that the same will happen with the next generation. We have a program until 2033 to achieve what we call fault-tolerant quantum computing. And next one. Okay, I think that today, eventually, where all these technologies were transforming the discovery with all these technologies that I've mentioned, the way that we do discovery, we can discover new materials, new technologies, new things. So this is my message for the end of the presentation. And going forward, I think at least we know very well that as Prometheus defies the Olympian gods, right, by taking fire from them and giving it to the humanity, the same happened with Icarus that flew too close to the sun to take the risk and show to people that they can fly, right? So always we have seen that human civilization made progress on the edge of mitigating the risks and breakthrough ideas. So with that message, I would like to close and thank you for your patience, and I'm open to any questions. Yeah.
Dionysios, thanks so much for the so inspiring talk. We learned a lot with our friends. We had a lot nice discussions. Okay, the future will be bright. I'm really happy that the young generation will meet several challenges. So the students, okay, maybe time maybe for 1-2 questions, if there is any from the audience. Okay, please.
Thank you for the presentation. Can you hear me? Oh. Yes. Thank you for the presentation. It was very nice. One question regarding the ISO you mentioned. Does this imply that probably there would be a move towards explainability in order to have better testing, or would you say more towards keeping it black box and just filtering the output, or something in between? Thank you.
Yeah, that is a nice question, right? I mean, because I think that in any case, in the enterprise world, right, the ISO will be the way that companies will be able to collaborate and make sure that they have models that they can trust. So the way that the ISO today works is that by creating a lot of different problems for the models, right? And they classify the error rate or the hallucination rate. And they want to keep a threshold, right, to make it ISO compliant. So this is how it works today. And of course, there are a lot of thinkings around that, how to make it harder, how to make sure that it will not hallucinate. But at least what happens is that when you train, right, what we have done, right, to train, to make the model ISO compliant, is that you can take the responses, you can feed them to an LLM as a judge in the training process and in the reinforcement learning process to allow your model to be ISO compliant, but at the same time make sure that you are not destroying the performance. So it's like a trade-off that you have to play in the training process to make the model compliant. This is how it is today, but of course this is an evolving field. I believe, my personal thinking is that enterprises will go to that direction to make all the collaboration with models ISO compliant.
Okay, one more. Okay, the last one. Okay.
We are really late.
Last one and stop. Okay, quick question, quick answer. 30-second questions, 30-second response.
Yes.
Okay. So there is a lot of discussion these days and a lot of work around a new technology that is called memristors. I believe that IBM was to a certain degree involved in that as well. So the question is, do we see hope from there, or this is something that it's not so promising anymore?
It definitely is. So very fast question answer. Thank you for the question, Manoli. Definitely it will be a technology that plays a very important role. We're also experiencing and having collaborations to realize the potential of this technology. But right now our efforts are around phase change material, phase change memory, and most of the focus of the work that we're doing on this domain is in analog computing. We can definitely discuss about the potential of memristors, after the talk. Thanks a lot.
Thank you, Dionysios. And an important announcement now from for the break.
So thank you very, very much for this presentation. It was really fascinating, and it covered, from ancient history to today. So really, thank you very much for all the connecting all the dots.